All right, guys. So here we're going to talk about how all those quantities now can be related to one another. Quantities like energy, the internal energy, amount of work done, and heat added. If you remember, I talked about Joule's experiment where he showed that mechanical equivalent of heat, where the energy that goes into increasing the temperature of water can be done by adding heat or can be done by doing mechanical work. That means one of the things we can do here is we can see that those things are related too, in terms of now we have two ways that we can change the internal energy of the system. And remember, when we change the internal energy of the system, it pretty much goes right away into changing temperature of the system, right? So internal energy of the system directly proportional to the temperature. So for example, change in internal energy is directly proportional to change in temperature. Now, one thing we talked about here is I can change the temperature by adding heat, right? So this equation Q equals mc times delta T. Now we also learned from Joule's experiment that same thing I can achieve by doing mechanical work. That means your system can have energy added either by heat or some kind of mechanical work. So we're going to use that to then derive this equation what that we call first law of thermodynamics, which takes into account a closed system. So let's say a system like this where you have some ideal gas in a container where there's a movable piston, and then let's say the bottom of the container is open, not necessarily open, but it's sort of like a conducting material that can interact with environment. So let's say I can put some kind of hot plate over there and use that to add heat into the system. Okay, so that means this is basically can be a hot plate which will add energy into the system, or it could be a cold bath which will remove energy of the system. That means you can have heat go back and forth. So this is, let's say, Q heat, right? It can go back and forth. So that means plus Q means energy, added, and minus Q means it's removed. So that means you can add heat or you can remove heat, which then directly will go into changing the temperature, which then will go into changing the internal energy. But also one thing we can do here is some of that energy, for example, can go, imagine, right? So there are those particles here inside the container. As they start gaining energy, then some of that energy will go into making them move faster. And as they move faster, they're going to start heating the piston. And it's a movable piston. It's not a fixed piston. So as they hit the piston, they can actually move it up. So the piston can actually, go up a little bit. And then what we can say here is some of that energy will go into doing work. So then internal energy will be changed by amount of work, let's say, that was done by the gas. So what we do then, we take all of those into account. That means we have two ways of adding energy or removing energy. So that could be in terms of heat or in terms of doing work. When we do work on the system, energy is added to the system, some kind of mechanical work, right? We do work on the system, energy is added. When the system does work, energy is removed. And the example of a system doing work is when those gases are, pushing the piston upward. They have to, use energy, right? You have to collide with the piston, and then they're gonna have to, push it upward. And that's the system doing work. So then what we have here is then internal energy. You can see, right? So basically we have Q, and we have work done, and this is basically two way of adding energy or removing energy. So let's say two ways we can change the energy of the system. So then those two kind of like combined together will give us this equation for the internal energy, where the internal energy is equals to amount of heat added or removed from the system. As I said, right, it can be plus if it's added or minus if it's removed, then minus work done by the system. So this equation specifically is for the work done by the system, because you might be able to also see that this is equals to Q plus work done, and if it's the work done on the system. So this equation can be plus W or minus W, and you have to be careful in terms of who's doing the work. Is it the external agent doing work on the system, or the system itself doing work? Because if the system doing work, energy is removed from the system. If the external agent doing work on the system, energy is transferred into the system. All right, so this equation is first law of thermodynamics. So it gives you basically, so like let's say you can see, right, uh, how to change internal energy of the system from this quantities like heat and work done. Okay, so you can see, right, again, this equation in either, minus work done by, let's say system, or plus Q plus work done on the system. Both of them can be, written for as a first law of thermodynamics. Okay. So now you can see, right, one of the things we have here is, um, if we then include all of the other types of energies, like let's say kinetic energy and then the potential energy, then this equation can be written in terms of changing kinetic energy plus changing potential energy plus changing internal energy, which will be then the energy of your system, and this is equals to Q minus W. Okay, so generally that's kind of what we have. But most of the time when we're talking about first law of thermodynamics, we only concern ourselves with the internal energy of the system. That means the change in internal energy of the system equals the heat transfer into the system, which is Q, right? Plus the work done by on the system, or heat transferred minus work done by the system. Okay. And what we have here is we're going to now look at several type of processes that are going to be in terms of changing the temperature of your system while keeping other things constant, or changing the volume of your system or keeping other things constant, or changing maybe several things together and maybe keeping just one, quantity constant. Remember, so we still have those, since it's ideal gas, right, we still have those system variables, right? So pressure, volume, number of moles, and temperature. Okay, that means as you start your system at some state, then you can do some kind of process, and it will change one or multiple variables at the same time. Okay, so we looked at PV diagrams, where PV diagrams can, allow us to see how we can represent that change in a two-dimensional graph, while actually we are keeping track of three quantities together. One thing we can have is that most of the time we can assume that n, which is the number of moles, or we can use that in terms of number of molecules, right? So since n is equals to number of molecules per Avogadro number, right? So this is something that we can assume that most of the time kept constant. So we are then looking at three quantities: pressure, volume, temperature. So this PV diagrams already give us pressure versus volume. So PV, which is pressure on the y-axis, volume on the x-axis. But then we also have temperature in this diagram as well, which is, you can see, right, are given in terms of those red lines. So those red lines represent what we call isotherms. So these are isotherms, which represent how temperature changes. So let's say this one line over here, right? So let's say this first line over there. This is not how temperature changes. This line actually represents one specific temperature. So let's say this could be 200 Kelvin, for example. That means going from here, right? So let's say from that point and going down like that. Let me use maybe a different color. So let's say going from here all the way down like that. That is a line for 200 Kelvin. That means the entire time, let's say if you're considering this point A prime or this point B prime, maybe somewhere over here C prime, doesn't matter, right? As long as it's along that what we call isotherm, the temperature of your system will be exactly the same. Now, same way, here we have another second line. So let's say here, because it is further from the origin, right, kind of moving in that direction, that's the direction of increasing temperature. That means you can see, right, the second line is actually higher temperature. I don't know, maybe like 250 Kelvin, which means that point A, which is, let's say, if my state is at point A, and I look at state at point B, so TA is equals to TB. That means temperature at state A is same as temperature at state B because it's on the same isotherm. Same way, temperature at A prime is same as temperature at B prime. They're also on the same isotherm. So I can always assume that my PV diagram can allow me to get three different information: the change in pressure, the change in volume, and the change in temperature as well. Because, for example, if I go from A to B prime rather than B, then let's say here's another process like this. Let's say if I go undergo that process, well, this process does this. There's a change in pressure because you can see, right, pressure A, pressure B prime are different. There's a change in volume because VA, VB prime are different. Then there's also change in temperature because temperature of A is greater than temperature of B prime. Okay, that means this process allows me to undergo all of those three quantity changes. Okay, that's why what we're going to do, we're going to look at some let's say processes that are let's say some kind of like specific to one variable to be constant the entire time compared to the others. So we're going to see that there are some examples where if I kind of start with that. So think like this. I already kind of mentioned one process, and that will be this. If I go from, for example, A to B, then this is specific type of process where I mentioned, right, the temperature doesn't change. So when you have a process where temperature doesn't change, that means I go from point A to point B. Okay. So I can see that for this process, my pressure changes and my volume changes. That means you can see, right, thing like this. So delta P is not zero and delta V is not zero, which means that there's a change for pressure and there's a change for volume. Okay. But delta T here is zero. Okay. So the process where delta T is zero means T is constant is known as a isothermal process. So isothermal process is a specific type of process where I can have my system change the volume, change the pressure, but the temperature doesn't change. Okay, so now let's look at this system over here and see, like, let's say, how can we have that? How can we change the pressure and change the volume, but for example, the temperature doesn't change? Think like this. For example, if I go from A to B, you can see, right? If I go from A to B, I can see that my pressure going from A, this is pressure A, and this is pressure B. Oops, B like that. I can see that this pressure B is less than pressure A. That means there's a decrease in pressure. If I compare pressure A and volume A and volume B, I can see that volume B is greater than volume A. That means there's increase in volume. Okay. So now what we can do here is this. If I increase the volume, pressure decreases. Well, we all know that already, right? That means imagine, right, let's say if this piston kind of moves right here. Okay. That means, I change my volume by this amount. So that's my delta V. Okay. So I increase my volume by that amount. And I know that pressure is inversely proportional to volume. That means if I'm increasing my volume, pressure decreases. Okay, fine. Pressure decreases, but we know already also that pressure is directly proportional to temperature. Well, if pressure decreases, temperature should also decrease, right? So right away, let's say there's sort of like, you know, um, seems like there's a disagreement with what we learned before. If I'm increasing volume, pressure decreases. Well, any change, if the pressure decreases, temperature should also decrease. But we're saying that temperature is constant. How can we have that? Well, we can have that because remember, this system is allowed to gain energy from environment. That means, think like this. If I put some kind of hot plate over here and add energy at the same time, let's say, while I'm doing this process. That means I'm increasing the volume, which decreases the pressure, but then I am also adding energy as a heat, which then increases the temperature. Okay, so because of the volume is bigger, the pressure is decreasing, but temperature is not decreasing because I'm constantly adding heat. Okay, that means it allows the temperature to remain constant, and in that case, you can you know go from point A to point B while maintaining the um, same temperature. Okay, so that's one of the ways we can do for this type of isothermal process. That means isothermal process is the process where the volume and pressure change, but temperature doesn't change. Okay, so in terms of then, okay, so right, in order for an isothermal process to take place, we assume the system is in contact with the heat, what we call heat reservoir. Okay, so all right, in general, we assume that the system remains in equilibrium throughout all processes. There are other processes that we're going to be looking at, and one of them is kind of similar shape as isothermal, but you have to be careful a little bit because isothermal, remember, assumes that you are going from, let's say, one state to another. That means from state A to state B along the same what we call isotherm, right? So think like this. So this is an isotherm. So this is an isotherm, and then here's another isotherm. Here's another isotherm. Let's say here's another isotherm. Those lines, let's say isotherms. And you can see, right, going from A to B is an isothermal process because we always go, you know, my line doesn't necessarily show that, but let's say it is that. So kind of going along that line. Okay. Where going from A to C is different because we are changing our volume, we're increasing our volume, right? So basically, pressure decreases. There's a change in pressure, which decreases, but also we are decreasing temperature. Okay, that means it's a process where those three things happen at the same time, and the shape kind of looks similar to isothermal, but it's not because we are going from one isotherm to another. So you have to be careful. We're going to look at this adiabatic a little bit closer later on, but that's kind of what we have. An adiabatic process is one in which there is, no heat, which will make sense, right? Remember, so here, the only reason the temperature was, constant throughout this process is because we added heat, right? Because we added heat in order for the temperature to remain constant. Okay, that means if I'm increasing volume to decrease pressure, if I don't add heat, the temperature will also go down. Okay, imagine if I don't have this, right? If I don't have, this reservoir, there's no added heat, the temperature would change. And that's what we have. So in adiabatic process, imagine there is no hot reservoir. That means if you're decreasing the pressure, it decreases the temperature. So that's why we go from, temperature at B to a temperature at C, where temperature at B is higher than temperature at C. Okay, that means without hot reservoir, there is no constant temperature. An adiabatic process assumes that generally this type of process happens so fast that there is no time for the, you know, let's say heat transfer into the system, and the temperature of your system, can either decrease or increase depending what you're doing. Because if you're doing expansion, that means you're increasing the volume. There's always decreasing, let's say, temperature. But obviously, one thing we can do here is this: we can also go in opposite direction. So let's say we can go like that. We can go from C to A. In that case, we're doing a compression. When you're doing compression, pressure increases, temperature increases, right? Makes sense. Okay, so think like this. One important thing about adiabatic process is that Q equals zero. Okay, so that's important thing. So Q equals zero. And then in a way, what you can think of here is that change in internal energy is equals to Q minus W work done by the gas. In that case, if this is zero, then internal energy is equal to the negative of the work done by the gas. So this is for the, how the first law modified for the adiabatic processes. Okay, now let's go back kind of looking at this one more time, because there's important thing that must be said about this type of isothermal process. So for isothermal process, we have this. We have going from A to B. Remember, for isothermal process, I'm going either from A to B or from A prime to B prime, right? The idea is that I'm staying on the same, isotherm. But we also know that internal energy, remember internal energy, let's say E internal, we looked at this earlier. So internal energy is equals to 3 halves nRT. Okay. That's the equation for, at least one of the equations, right? We can also write it in terms of, KT, NKT, right? But this is the internal energy equation. And you can see that if I'm looking at change in internal energy, this is equals to then 3 halves n R times change in temperature. So if I have then, for example, right, isothermal process, if I have an isothermal process, then my change in internal energy is equals to Q minus W, which is the work done by the gas. Okay. But according to this, this equation over here, right, where I can say that internal energy is equals to then 3 halves nR delta T. Well, if I'm going from A to B, my delta T is zero, right? Remember, my delta T is zero, which means my internal energy here is zero. Change in internal energy is zero. Why? Because internal energy only depends on change in temperature. If you do not have change in temperature in your system, your internal energy doesn't change, which means if I come back to this equation, I can say that this is equal to then zero. That means left side of the equation is zero. So Q minus W is equals to zero, which means Q is equals to work done by the gas. Okay. That means in order for you to stay on the, as an isothermal process, how much you add goes exactly into the how much work is done. So no extra energy added to your system or removed. In order for this charges, not charges, like let's say the particles, right, to move the piston upward, then they gain that energy, right, in order to do that from heat. How much energy you add as a heat goes directly into doing work. And energy of the system, right, internal energy of the system does not change because there is no change in energy, there is no change in temperature. Okay. That means this is, kind of like important outcome of the isothermal process. Internal energy, change in internal energy is zero. So then amount of heat transfer is equal to the amount of work done by the gas. Okay, so then we can see here is adiabatic process. There is a change in internal energy because there is no Q, right, to kind of take care of the W. So there is no Q. So then there is a change in internal energy because of the work done. And in this case, you can see that what you have here is there's either an increase or a decrease in temperature. Because if you go from A to C, there's a decrease in temperature. If you go C to A, then there's an increase in temperature. And you can always assume whatever the delta T you have, exactly same way your internal energy changes. That means if your delta T is positive, that means your change in internal energy is also positive. If your delta T here is negative, then your change in internal energy is also negative. Okay, because they are directly related to one another. Decrease in temperature decreases internal energy. Increase in temperature increases internal energy. All right, so now we can talk about then two other processes. One is known as isobaric, and that's when you go from A to B. So basically, you're here at state A. Now, again, what do I mean by state A? So you have certain pressure, volume, and temperature, and then we say that, okay, so when you have certain pressure, volume, and temperature, let's define that to be state A. So this is PA, VA, TA. So that represents basically this, right? All right, something like that. Okay. So that's the blue line is the isotherm. Then you have the pressure A, and then you have volume A, and then temperature A. Okay. Then you undergo a process. That means if your process goes from A to B such that during your process, you can see, right, your pressure remains constant. That means if you come back and look at, you know, PB, you can see, right, that it's exactly same as PA, same pressure as, you know, before and after. So this is known as a isobaric process. Isobaric process occurs at constant pressure. That means your pressure changes. But obviously, if I look at then my volume, I can see that I have VB. Well, my volume doesn't change. That means VB is not equals to VA for the isobaric process. And I can also see, right, that I'm going to go and hit another, isotherm. That means my temperature will also change. TA is also not the same as TB is not the same as TA. So volume changes, temperature changes, pressure remains constant. And it's always going to be a horizontal line like that. That's an isobaric process. That means during this process, your pressure remains constant. But if the pressure remains constant, other factors will have to change, which is, you can see from this type of, kind of going back and looking at this, system. So here you have that gas, right? And that's the movable piston. So the question here is, how can we change the volume and change the temperature and the pressure doesn't change? Because we know, right, that pressure is directly proportional to, or directly proportional to temperature, and pressure is inversely proportional to volume. If I change the volume, pressure should change. If I change the temperature, pressure should change. Well, again, we can do that by putting some kind of, hot reservoir or cold reservoir. Imagine what I have here is this. If I am, for example, right, if I'm pushing the piston down, so let's say the piston moves downward. So let's say right here. Now this is my position of the piston. I can see, right, my volume goes down, which then increases pressure. Okay, because now smaller area for those molecules to collide and things like that. So pressure increases. But I'm going to put here is cold reservoir, which then removes energy. Well, if it removes energy, that means, I'm removing heat. So then the temperature will go down. Well, as temperature goes down, the pressure goes down. So then when you add those two things together, where you basically compressing, which increases pressure, but then removing heat, which then decreases temperature, which, right away automatically, right, decreases the pressure. If you do it such a way that they're proportional, how much you compress, that means, let's say how much you change the pressure due to the compression is exactly if it's same as how much you, let's say, remove heat and decrease the pressure. You can see, right, if you add those changes together, you're going to get, constant volume. That means there's no change. That means how much you decrease by one way plus how much you increase the other way, that changes cancel each other and you have constant pressure. So that's how the isobaric process works. That means any type of effect for pressure from, let's say volume is canceled out by, let's say the temperature, by heat, which you can see, right, other way around can also be true. If you are, let's say moving it outward, like let's say expanding, that means volume is increasing, pressure decreasing, then you can add energy, right? You can put a hot reservoir, which then increases temperature, and that increases pressure, and then again, effect cancels out. Okay, so that's kind of like one of the things we can do. The next one here is what we call isovolumetric. Okay, so this one here is assumes that here's your, state A. So you have pressure A, volume A, temperature A, and then you undergo some kind of process. So let's look at this type of process. So let's say here's your piston. So then let's say this is your volume A. Okay. By the way, here what we had is that this was their volume A. And let's say this was then volume B, right? You can see that there was a decrease in volume. So let's say, okay, so that's your volume A. Remember the volume here will be the height times the area. right? So let's say that's how we can find the volume. So think like this. So what we do here is we undergo a process, and we can see that, let's say, in terms of then my isotherms, so let's say this will be one isotherm, then this will be another isotherm, and maybe here is another one, and so on and so forth. So one thing we can see from here is if I go from A to B, my pressure A is, sorry, pressure at B is not equals to pressure at A. And one thing I know here is this, right? So as the pressure is decreasing, temperature will decrease. Okay, so temperature will decrease. Okay, so as the temperature decreases, the idea here is that if you have a same container, let's say, right, you have a container like that with a gas. So what happens, let's say, to change the pressure, how do we change the pressure without changing the volume? Well, think like this. So this pressure was for this volume and for this specific temperature. If my volume doesn't change, that means same before and after, the only way I can change the pressure is if I change the temperature, right? That means if I put, for example, here, see if I go from A to B in this direction, that means I go from A to B that means I'm decreasing my pressure. It can only happen if I put here some kind of cold reservoir, which then removes heat. If I remove heat, temperature goes down. If temperature goes down, pressure goes down without changing volume. Okay. That means in this case, I can assume that, there is a Q, right? So there's a Q. And what I have here is change in internal energy is equals to Q minus work done by the gas. But there is a, change in energy, right? I'm removing, let's say, the heat energy. But piston doesn't move. There is no expansion. There is no, let's say, the volume basically doesn't change, right? And if the volume doesn't change, that means there is no work done. That means in this case, this guy here is zero. That means my change in internal energy is equals to the Q. Okay. So that's one of the things we're going to see is that for the isovolumetric processes, the internal energy is equal to the amount of heat added, because how much I remove energy directly goes into just changing the temperature, right? Because none of the, let's say, gases are doing work, or no, basically nobody compressing or expanding, right? Which means that external, or the work done by the gas or on the gas is going to be zero. Okay, so that's kind of, one of the things we have over here. Okay. All right, so and obviously you can see, right, if you're looking at the isobaric, change in internal energy is equals to Q minus W. Well, one thing we did say is that there was, there is a need for the Q, right, in order to keep the pressure constant, but there's also need for the W. So it's basically Q minus W. That means we have both, right? There's a, heat added or removed, and also the work done by the gas because there's a change in volume. Okay. So those are the, in terms of, hopefully you guys can see how those things are related to one another. Okay. So let's go to the next one over here. So this one is sort of like, let's say, summarizing everything that we talked about, and also showing that how can then we calculate the work done. We know how to calculate the Q. It's mc times delta T, right? Assuming that what we're doing here is just changing temperature, right? Let's say we don't have a some kind of substance over there that's gonna have a change in phase during these processes, just a change in temperature. And Q is equals to mc times delta T for a solid and a liquid. So if you have a solid or a liquid or even, let's say, a gas, this equation technically can be applied. Okay, so we're going to see that generally when we go and talk about real gases, this equation can change a little bit depending on what you have. But for now, let's say that here's the equation for the Q. But for the W, I mean, we had this equation, right? W equals to integral of F dot dl. So that's one equation that we learned before. So which is a dot product between force and length element. Well, it's still the same equation, right? It's still the same equation. It's just we're going to modify it a little bit for using, let's say, are variables of the system variables rather than some kind of force, which technically there is a force, right? In order for you to compress or expand, you need to apply force. But the idea here is this: if there is a compression or expansion for your system, that means, let's say there's this piston here, right? Either moved out or inward, right? Outward or inward. So there's going to be, like, let's say, this delta L, which is the amount of change that we can have. Okay. And what we can do here is then dW, right? The amount of work done that goes into changing this small dl amount is F dot dl. Okay. But also we know that force is pressure times area because force is, remember, the pressure was force per area. So force is pressure times area. That means if I take this and I replace by, force with pressure times area, then force, which is pressure times area times then dl. Well, dl becomes nothing but, ADL. Remember, I told you, I think previous slide, is the volume here is, so the total volume is area times total length. But if you talk about this small change in length, right, that means, whatever this dV changed by how much that volume changes. So this will be then ADL. Okay. That means this ADL is nothing but dV changing volume. So we're looking at, how much work goes into changing the volume by that, a small amount. Okay. Now from here we can pretty much, let's say you have this equation, right, that gives you the work done. Okay. So we can see that all we have to do here is we write this as dW is equals to P dV. Okay. So here then we can just basically use this sort of like a basis for work done for most of those, let's say, processes that we looked at. Okay. So for example, let's start with uh, isothermal process. Okay. Isothermal process, remember, assumed that, so let's say isothermal, assume that pressure changes, right? There's a delta P, there's a delta V, but T remains constant. Okay. So now let's look at in terms of what we can do with that. Okay. So by the way, so you know that, right? So going from here to the X, we just basically take the integral of both sides, and here we have W. So W is equal to an integral of P dV going from V1 to, let's say, V2, or VA to VB, right? So, but like, let's say just state 1 to state 2. Okay. So then what we have here is this. So this is our equation. Work done is equals to the integral going from state A to state B, P dV. But pressure is also, according to the ideal gas law, is equals to nRT over V. So what we do here, we take this pressure and we replace it with that. Okay. That means once the pressure is replaced with nRT over V, nRT is just a constant because n is a constant, R is a constant, and T is a constant for this specific process because it's an isothermal process. Okay. Then inside the integral, we just have dV over V. dV over V, if you hopefully remember, right? 1 over x dx. If I'm doing the integral of that, this is just going to be then ln of x. Okay. And that's what we have, right? So we get ln, and since we have VA and VB are the limit of our integral, so let's say if you have 1 over 2, ln of x 1 over 2, this will be then ln t over 1. Okay. So our equation becomes nRT times ln of VB over VA. That's for the isothermal process. That means the work done is equals to nRT ln of VB over VA only for the isothermal process. Also, one thing we have is, if you look at this equation over here, if the work done is the integral of a PV, let's say diagram, then you can say that if you have this process going from A to B, then the area under this curve is exactly going to be equal to this, whatever you calculate using this equation. That means you can do two things: either calculate work done by using that equation, or know that work done is always area under the graph, area under the PV graph. Okay, but not every process is going to have this equation. Again, this is equation specifically, right, for the isothermal. And then what we can see here is that let's say if you have a system going at state A, let's say, then you can go to state B actually taking different paths. One will be that direct isothermal process, right? Go from here to there. That means that's one thing you can do. Starting from here, go to B, taking this isothermal process. That means taking that path. Okay. Now, the amount of work done will be this, right? So that's the amount of work done if you take that isothermal process. But there are more ways, right? You can go to, from A to B. And let's say one of the ways you can go here is going from A, you can go to D, which is an isovolumetric, process. And then from D, you can go to B, doing an isobaric process. Okay, now, also you can do, so let's call this path 1, let's call this path 2. Then you can also go isobaric. Let's call this D for, I already have, so let's call this F. So you can go from, A to F, and then from F to B. That means you can do like the way around, right? So let's call this path 3. So path 1, isothermal from A to B. Path 2 is isovolumetric from A to D, then isobaric from D to B. Or path 3, which is isobaric from A to F, and then isovolumetric from F to B. Okay, now, what are the differences? Seems like the end result is the same. Yes, end result is the same. But how much work we do for each path is not the same. Depending on how much, work you do, right? Basically, will determine how much internal energy, let's say, is used, or how much of that energy is used for that type of, work on by the gas or on the gas. At the end of the day, if you talk about, right, change in internal energy, is this, going to be different depending which path you're taking? Well, the answer here is no. Look at change in internal energy. Well, change in internal energy is the energy at point A compared to energy at point B. Because A and B are on the same isotherm, this is going to be zero, and it's going to be zero regardless if you take, path 1, 2, or 3. Your change in internal energy is zero because you go from A to B, both of them are on the same isotherm. Okay. Now, but in terms of then amount of work that you do will be different because, for example, I showed you here that this is the amount of work done that will be that will going from A to B using the isothermal process. That means all of this is the amount of work done. If you go from A to D, then D to B, which is path 2, then only this is the amount of work done. And you can see, right, compared to that, you have more work done if you go from, A to B doing the, let's say path 1 than path 2. And if you take path 3, you're going to have to do even more work. So that's why work done using path 3 is greater than work done using path 2, path 1. Okay, I can't erase. So that is greater than work done doing path 2. That means path 2 is, the more efficient in terms of the amount of energy goes into work. Okay, that means you can achieve the same thing by breaking it down into two different paths, let's say, or, two different, let's say processes, but still, ended up getting the same state B while, spending less energy on amount of work done. Okay, so that's kind of what we have. All right, so and also the calculation for this is much simpler because the calculation for the, let's say, isovolumetric. So let's see what is the amount of work needed to go from state A to B taking path 2. Because we already know, so kind of let me make it a little bit cleaner. Remember, I already gave you in terms of the So let's say this is path one. Path one is equals to, um, so basically this is nothing but integral of P dV going from A to B. And as we saw, we had to integrate this, right? We had to integrate to get nRT ln VB over VA. Okay, so technically it requires a integration. If I go path two, for path two, then what I have is that first I go from A to D, and go from A to D is isovolumetric. So here's what I have for that one. So work done from A to D is equals to integral of P dV. Okay, but I can see one thing is that there is no change in V, which means this integral going to go to zero, because if I don't have change in V, then this integral basically will go to zero, which means there is no work done for isovolumetric process, which we already saw that earlier, right? So then work done is zero because of this. You can also see that mathematically. Then if you go D to B, so then work done going from D to B is this. So integral P dV, but for this process of isobaric process, right, the pressure is constant. I can remove the integral. So it becomes just integral of dV going from dA to VB. That means work done going from D to B is equal to just nothing but P times delta V. That's it. Okay. So P times delta V. That means that net work is equals to then work done but from A to D, which is zero, plus work done from D to B, which is just P times delta V. You can see, right, how much simpler it is to calculate the equations for path two compared to path one. Okay. Well, same thing. What we have here is this for the isobaric and first you do isobaric and then you isovolumetric. The only difference here is, here we are using pressure, at B, right? So we're using pressure at B to do this calculation, where work done for path three will be zero plus, so this part is still zero, right? But then work done for this, from A to F will be then PA times delta V. Since delta V is still the same, but PA is higher than PB, you can see then you're going to do more work for that path three. All right. So in terms of then what we have is that as conceptual example, work in isothermal and adiabatic processes. So reproduced here is the PV diagram for a gas expanding in two ways, isothermally and adiabatically. The initial volume VA was the same in each case, right? So let's say here's VA. Okay. And the final volume were the same, VB equals VC. That means, this is also, VC and VB. They're the same as well. Okay. That means same delta V. Now the question is, in which process was more work done by the gas? And I'm really hoping that at this point it will be clear to you that more work will be done going from A to B than going from A to C. And that simply you can see that, let's say this is the amount of work we need to do for going from A to C. And then this is the amount of work that we need to do to go from A to B, which is bigger area, larger area means larger amount of work done. So work done going from A to B will be more than the work done to go from B to C. Okay, so it's higher amount of area. Okay, so summarize everything. So we have an isothermal process. Temperature remains constant. Delta T is zero, which makes change in internal energy zero. Because of the change in internal energy, again, is equals to nRT, 3/2 nRT delta T, let me put it like that. And if the delta T is zero, change in internal energy is zero, which means Q is equal to the work done. Then we have an isobaric process. Here pressure is constant. Well, in this case, we have both Q and we have W. So you can then calculate the amount of heat added, for example, by calculating change in internal energy plus work done. Probably the easiest way to do that. So in this case, because pressure is constant, you're probably going to be given what is the change in temperature, and then you can use that to calculate change in internal energy. And if you know that change in volume, then you can use that, let's say, to calculate a work done. And then internal energy, change in internal energy plus the work done by the gas will give you an amount of heat added or removed during the process. Okay, so that's one of the ways you can just kind of go around solve problems in this type of process. Then we have isovolumetric. So isovolumetric, volume constant, which means delta V equals 0. Well, delta V equals 0 means there is no work done. The work done is basically, remember, is to give you expansion or compression of your system. It means change in volume. There's no change in volume, there is no work done, which means that all that energy will go either in increasing. So that means if the heat added, it will directly go into changing changing temperature, which directly changes internal energy. That's why we can say that they're related. Okay, so adiabatic is the last one, which is, remember, there is no heat added or removed. There is Q equals 0 for this process, which means that change in internal energy is equal to negative work done. Okay, so remember, the Q equals 0. Okay, so the Q equals 0, right? And change in internal energy is equal to then, Q minus work done. So since this is 0, remember this is still work done by the gas. All right, so that's kind of what we have. So we're ready to solve some problems here. Okay, so how much work is done on the gas in the process shown in this diagram? All right, so we can see we have a PV diagram where we have, initial here and then the final over here in terms of, let's say, would you recognize what type of process is this? Let's say if I separate this into, I don't know, 1 and 2, can you recognize what is 1, what is 2? Well, not really. It's neither it's not isovolumetric, not isobaric, not isothermal, none of those things, or adiabatic, right? None of those things. But one thing we have here is we know VI, okay, which is basically 200 kilopascal. Sorry, I meant to say PI. And then we know P. Let's say what we can do here is we can kind of like have another one right here, kind of like, let's say we can see that it goes maybe we can put like something here, I don't know, A over there, right? So from I to A, from A to F. So so VA here is equal to then 400. I keep doing that. So PA is 400 Pascal, kilopascal. And then P final here is 200 kilopascal. Okay. So then we have the same thing for VA, so VI, which is 300 cubic centimeters. And then what you have here is V final, right? Which is 100 cubic centimeters. Okay, now, are we find the work done? Well, what we do here is we find the area under the graph. The way we find the area under the graph, we break it down into 2 parts. Okay, so we can say that here's a triangle and here's a rectangle. And what we need to do is just basically, calculate the work done for that. Okay, so from here, what we can do here is we can solve it where we can say then the work done on the gas. So think like this. So here we have this equation, right? So work done is equals to integral of PdV. This is if the work done is by the gas. Okay. If the work done on the gas, it then equals negative of integral PdV. By the way, this is from V1 to V, or V initial, V final, and put it like that. It's negative if it's on the gas. And that's the question, is how much work is done on the gas. So which equation to use will determine on, let's say, what given to you. We want to know what is the work done on the gas. That means we use this equation. Okay. So using this equation, um, by the way, the negative comes from the fact that um, when work done is positive, when you remember, when you do work on the gas, you are pushing the piston, inward. So the volume decreases. When the work done by the gas, then gases push the piston, so then it expands. That means that's why when the work done is when work is done on the gas, your volume decreases, but your work done on the gas is positive, and that negative basically represents that. That means when the work is done on the gas and it's positive, the volume then decreases. Okay, that negative basically represents that. Okay, so we're going to be then using this equation. So work done is equals to, so negative going from P initial to V initial to V final. Okay, so P dV. So then this is going to be in terms of negative. So you can see, right, going from P initial to P final. So technically your pressure here is constant. It doesn't change, right? And then you have then dV going from V initial to V final. So this becomes negative P times delta V, like that. So then work done is equals to negative. All right, so then what we have here is the areas, remember, so kind of like you're looking at in terms of how to get, so the area of this part times the area of that part, right? So you can kind of like think like this. It's just in terms of what you have here is finding the area. So let's say in this case, so rectangle portion will be 200 kilopascal times 10 to the 3 Pascal. Okay. Times then the volume change, and that's basically from 300 to 200. So this will be 200 times 10 to the, since this is centimeter cubed, we have to convert it to meter cubed. So it becomes -6 meter cubed. But since we are compressing, this is going to be negative. Okay. Then plus, then the second area, which will be, the triangle. So then this will be basically 1/2 times change in pressure, which is 200, times 10 to the -6 Pascal. Oh, sorry. So this is 10 to the 3 Pascal. Then times 200 again, right? So 200 times 10 to the -6 cubic meters. Okay. So we basically have that. And since in this case, our pressure, so basically we have pressure, we have volume, right? So there's also a negative over there. Okay. And those negatives, eventually going to cancel that negative in front that we have. And the work done will be equals to, if I do the calculation, will be 60 joules. Okay. So in terms of then what I have here is that the work done is going to be positive because this is the work done on the gas. And every time you have a compression, work done on the gas will be negative. Work done on the gas will be positive. Work done by the gas will be negative. That means the environment does positive work on the gas whenever it is compressing. All right, so let's look at another example here. So we have 2 mole of gas are at 30 degrees Celsius and a pressure of 1.5 atm. So how much work must be done on the gas to compress it to 1/3 of its initial volume at A, at constant temperature, and B, at constant pressure, and C, we're going to show both processes on a single PV diagram. Okay, so let's see what we have. So we're given number of moles, right? So let's use this color over here. Okay. So we're given N is equals to 2 moles. We're given temperature at, let's call this TA, and that's 30 degrees Celsius. But remember, we need to convert it to Kelvin. So 30 degrees Celsius plus 273. So this should give us in terms of 303 Kelvin. And then the pressure is 1.5 atm. So we technically going to need to convert it into, let's say, a Pascal. But, we can wait for that right now. But we need to eventually, right? So whenever, you can do it, either, unless we can just keep things in terms of, let's say, ATM. Okay. So let's say those are the initial values, and then we want to say how much work must be done on the gas to compress it to 1/3 of its volume. That means, let's say, remember, this is PA, then we have VA. Then what we have here is when we have VB is equals to 1/3 of the VA, right? So that it compresses to 1/3 of its initial volume. Okay. So for this one, we can see that in terms of equation that we have, we are assuming that for part A, this is done at constant temperature, which means it's just an isothermal process. Okay. And the work done, we can pretty much right away start, PV diagram, right? So let's say if this is our A, remember we are compressing. That means we're going to go from VA to some VB over here. Okay. So 1/3 of its volume. That means if it's isothermal, it has to be on one of these lines, along one of these isothermal lines. That means my point B is right here. Okay. That means my TB is equals to 303 Kelvin. Okay. And then one thing I can do here is I can calculate the work done for isothermal process, which is, if you remember, right? So we have that um, integral of PdV going from VA to VB. And then P is changing, right? P is changing. So, but I can replace it with nRT over V. dV, which then allows me to take out nRT and then integrate dV over V, going VA VB. Remember, so this basically gives me nRT ln of VB over VA. Okay, so I can then calculate this. So 2 moles times R, the constant, which is 8.31. By the way, so this was work done on the gas. That means I should not forget the negatives there. Okay, so 8.3 joules per mole Kelvin, then times ln of VB over VA. I forgot 2303 Kelvin. So ln. Now, what I have VB over VA, well, VB, VB is 1/3 of the VA. That means if I do VB over VA, I'm just going to get 1/3. Okay, so that means that ln of 1/3. So calculate the work done. We get 5.5 kilojoules. Okay, 5.5 kilojoules, because if you do ln of 1/3, you're going to get negative. It's going to cancel out. You're going to get a positive value there. Okay, so this is for part A. So then in terms of finding the work done with a constant temperature, remember, right? So we are pretty much using this equation, and that's how you derive it. Part B, it says constant pressure. Okay, so for constant pressure, what we have here is, let's do this for part B. Okay, so for constant pressure, we have work done is equals to negative VA to VB. Remember, so PdV, but constant pressure means that, just pressure comes out, that integral just becomes delta V. Okay, that means negative P times VB minus VA. Okay, remember, so we still assume that we are doing this change in volume, 1/3 of its, that means work done is equals to in terms of pressure times change in volume. So it's going to be then negative P times, well, VB is 1/3 of VA, then minus VA. Okay. So, and from here, we can say that this is equals to, so if I do negative P, so over here, 1/3 of VA minus VA, I get 2/3 of VA. Or negative P, or negative 2/3, P times V. So PA times VA, basically, right? PA times VA. Well, that's one thing I know here is PV is equals to an RT, and this is nothing but that, right? P times V. That means it's equals to negative 2/3 times an RT, which will be easier for me to calculate. Then I can say it's negative 2/3, 2 moles, 8.314, then times 303 Kelvin. Okay. And I can calculate this work done to be 3.4 kilojoules. Okay. And to this diagram here, what I have is this. So the idea is, let's say at this point, for the isothermal process, right, the volume, when it's decreased by 1/3, that means, when we got to this point, when we got to here from A to B, I can see, right, so my volume decreased, right? So basically VB is equals to 1/3 of VA, but at the same time, this is my PA and this is my PB, my pressure increased by how much? Well, exactly, 3 times, because they're related, right? How much you change your volume, exactly same amount or same proportional, right, changes your pressure, because temperature remains constant. None of that goes into, let's say, temperature. So that means what we have, you can say that PB is equal to 3 times PA. Okay. So PB equals 3 times PA, and since I have 1.5, so this should be then 4.5 ATM. All right, so that's basically will be my other process, right? If I do the diagram, it will be like that. Okay. So, all right, let's look at then one more example. So we have a gas that undergoes 2 processes. In the first, the volume remains constant at 0.2 cubic meter, and the pressure increases from 2 times 10 to the 15 Pascal to 5 times 10 to the 5 Pascal. And then the second process, I think that's about it. The second process is a compression to volume of 0.12 cubic meters from 0.2. So at a constant pressure of 5 times 10 to the 5. That means in one, we we keep the volume constant. So it's a volumetric process, right? Keeping volume constant, increasing pressure. And then the second one, keeping the pressure constant and increasing the volume. Okay. So part A says in a PV diagram, show both processes. All right, so let's look at that. So this is going to be our PV diagram. And this will be my state A. So first I'm going to do, so I'm going to say that VA, so this is my VA and PA. And then I keep the volume constant and increase my pressure. So it's going to be isovolumetric like this. So let's call this, going from 1 to 2. Or, I already said A. So let's say going from A to B. Okay. So, and then you go from B to C. Like this, go from B to C. So the A to B is a isovolumetric process, B to C is an isobaric process, and that's basically how to do that. So this is my P which is same as PC. So PB is equals to P point C, which is 5 times 10 to the 5 Pascal. PA is equals to 2 times 10 to the 5 Pascal. VA is equals to 0.2 cubic meters. VB is equals to VC, sorry. So VC is equal to then 0.12 cubic meters. Okay, so those are the values of what I've given. Part B says find the total work done by the gas during both processes. All right, so I'm hoping you will be more comfortable this time around to look at those. So let's say going from A to B. Okay, so this is isovolumetric. And then we know that work done for this process or work done for the isovolumetric, right? So is always equals to 0. Okay. Sometimes this is also known as the isochoric process. So isovolumetric or isochoric is basically 0. Why? Because work done is equals to P times, integral of P dV. There is no change in volume. So you get 0. Then going from B to C, so you have an isobaric. Okay. So it says find the total work done by the gas. So this is important, by the gas. That means I can say work done is equals to integral of P dV, going from VA, let's say VB to VC, right? So this one is pressure constant comes out. Then I have dV going from VB to VC and becomes P times delta V. Okay. So that means work done is equals to pressure is 5 times 10 to the 5 Pascal, and change in volume. So it's a compression, right? Going from 0.2 to 0.12. That means final is 0.12 minus 0.2. And so that's technically going to give me a negative number. So I'm going to get then negative 4 times 10 to the 4 joules. That's going to be my work done. So then if I look at then total work done, the net, so that's, this is 0. This is negative 4 times 10 to the 4. That means it's negative 4 times 10 to the 4 joules. That's my total work done by the gas. Again, why is it negative? Because when the gases do work, but there's a compression, that means, it's a negative. That means for the compression, work done by the gas is negative. For the compression, work done on the gas will be then positive. All right, another example here. During the time 0.305 mole of an ideal gas undergoes an isothermal compression at 22 degrees Celsius, 468 joules of work is done by the surroundings. That means that's the amount of work done on the gas, right? On it, by the surroundings. If the final pressure is 1.76 atm, what was the initial pressure? And then sketch that in in the PV diagram. All right, so we're given the number of moles, 0.305 mole. We're given the temperature, 22 degrees Celsius plus 273. This will give us 295 Kelvin. Okay, that means, remember, so always must convert it into Kelvin. We're also given the work done on the gas, and that's 468 joules. So you can say also work done by the gas and be negative 468 joules. So depending which one you're using, right? Okay. So then part A is asking if the final pressure is 1.6 atm. That means, we can assume that this is, let's say, TA, okay, and PB is equals to 1.76 atm. What was the initial pressure? Okay. Now, what type of process is this? Well, it's an isothermal process. What does it mean? It means temperature at B is same as temperature at A. Okay, so now that we know that, That means we can say that those are our initial values. So for part A, what I want to basically calculate is my final pressure. Okay, calculate my final pressure. Okay, now in terms of then what I have here is I'm given amount of work done, right? Instead of like, let's say, amount of, let's say the volume or something. I'm given amount of work done, and I can say then work done is equals to nRT, right? So basically, remember, so this is just P dV, integral of P dV going from VA to VB. Okay. So then we can replace this with the nRT, integral of dV over V going from VA to VB. Okay. Then from what I have from here is then nRT, then it becomes ln of V2 over V1. Okay. Remember, one thing we're not given is any information about the volume. Absolutely no information. We don't know initial volume. We don't know the final volume. Okay. But one thing we have here is the final volume over initial volume ratio. So let's say if you can think about it, right? So this is let's say V1. So think like this: P1 V1 equals nRT1, and P2 V2 is equals to nRT2. So let's say something like this. Then from here we can see that, for example, here's a ratio of V2 over V1. That means if I take this and let's say, or other way around, right? Basically divide the second one by the first one. That means divide this by P1, let's say P1 V1 equals nRT1. So doesn't matter A or B or 1 or 2, just easier like this right now. Here's what we have. Right away you can see that NR cancels out, but T is the same before and after as well. So then this also cancels out. That means what we have is this: P2 V2 over P1 V1 is equals to 1, right? Equals to 1. That means if I rearrange, this will be, I will have this: V2 over V1 is equals to then P1 over P2, right? Because number of moles doesn't change, temperature doesn't change, then I get this ratio. That means V2 over V1 is same as P1 over P2. All right. Okay, so hopefully it's clear. That means we can come back over here. Then I can say that this is same as nRT ln P1 over P2. That means I'm replacing this ratio of V1 over V2 over V1 with the P1 over P2. I don't know any of those things, but here I have second one and I want to find the first one, and that's it. That's all I need. I basically eliminating the the ratio of the volumes. I'm substituting that with the ratio of the pressures. Then I have that work is equals to nRT ln P1 over P2. Divide both sides by nRT. Then what I have here is this: work over nRT is equals to ln P1 over P2. Then in order to get P1, P2 out of, from that ln, right, I take the E for both sides, right? So then on the right side, E of ln P1 over P2 will be just P1 over P2. On the right side, then I will have E to the, work over nRT. Okay. But, what I have here is, it's not something that, is an issue right now, because then P1 is equals to P2 times E to the work over nRT, and I have everything, right? Remember, so I have P1, which is 1.76 atm right here. And then E to the, then I have work done. Well, work done is basically, remember, if I'm talking about on the gas, 4.868. If I'm talking about by the gas, then it is negative 468, right? So let's use that. So it's then negative 468 over the N, which is 2 moles. Sorry, Previous one was 2 moles. So 0.305 moles, then R 8.31 far, and then the temperature is 295. Putting everything together, right? So for that, calculate pressure 1, and that will be 0.942 atm. Okay, that means I can get that value for the initial pressure, and we can see, right, there was an increase in pressure, right? There was an increase in pressure because it was a isothermal compression. That means if I'm looking at the diagram, so not much room, but I can do it right here. So if I have PV diagram, I can see that I started with, low pressure right here, and it's an isothermal process. So like that, right? So I start from here. This is my A, and I go somewhere over here, which is my B. Okay, along the same isotherm. So my pressure increased, and my volume decreased. VA, VB. That's why it's a compression. Every time you have a compression, you will have then increase in pressure. And if you have a constant temperature, then it's going to go through one of those isotherms. All right, so that's kind of what we have. And here's one more example, one last example in this section here is, so we have a process, ABC, shown in the PV diagram, involves 0.0175 mole of an ideal gas. So we want to know what was the lowest temperature the gas reached in this process, and where did it occur. Okay, and then how much work was done, and by or on the gas from A to B, and then from B to C. And then if 215 joules of heat was put into the gas during ABC, the entire process, how many of those joules went into internal energy? Okay, so let's see what we have. Okay, so again, the first one was asking where do we have the lowest temperature during this process? Well, remember what we have here, the isotherms, they go like this, right? Okay, and closer you are to the origin, lower your temperature. And since we're asking for the lowest temperature, it will be here at TA. So the TA is lower than TB, which is lower than TC. So TA is the lowest temperature. Okay. So then what we have here is part B. Well, actually, one thing we can do, we can even calculate this, because the ideal gas law equation, PV is equals to nRT. So this is then PA, VA, nRTA, and we're given everything, right? You can see, right, TA is equals to PA, VA over nRT, nR. So pressure is 0.2 atm. Okay, so here's what you can do. You can either use that R, which is the constant that given in terms of, let's say, the ATMs and liters, right? So you can use that gas value of that, or you can convert everything into, let's say, Pascal and cubic meters. So up to you. So for example, in the solutions, right, in the slides, I have it in terms of the converting everything into SI units, Pascal and cubic meters and things like that. Let me do here using the other version so you guys can see the difference. That means keeping the pressure in terms of ATM, keeping the volume in terms of liters, but then dividing by number of moles. I think number of moles was 0.0175. But the constant now I'm going to use 0.08206, and this one liters ATM, then over Kelvin mole. Okay, so you can see, right? ATM cancels, liters cancels, number of moles cancels, and then 1 over Kelvin gives you the temperature. Okay, that means if I do this calculation, I'm going to get 278 Kelvin. Okay, using that. If you convert everything and calculate using SI units, you're going to get the same thing. Part B was asking how much work was done by or on the gas for all of those, AB, from AB to BC. Okay, so let's look at them. Let's say for this one, first one, right, going from A to B. Okay. Well, work done going from A to B is integral of P dV going from, let's say, A to B, right, or VA VB. But we can see that VA and VB are the same, so we get 0. That means work done equals 0 for this, from A to B. B to C. Well, let's see with B to C. What do we have? Well, it's neither of those, right? It's neither, isothermal, adiabatic, or, isovolumetric. So the one way we can do that is if we find the area under this graph. Okay, find the area under the graph. And that's kind of, what we can do. Again, kind of separating this into two areas and then just finding the value. So from here, we can say then the work done is equals to, so 1/2 0.5 ATM plus 0.3 ATM, then times 6 liters minus 2 liters. Okay, so that's basically, calculating the work done. And here is equals to, so 1.6 liters times ATM. So 1 times 10 to the negative 3 cubic meters per liters. Then 1.013. Now we're converting everything, right? So that's basically that's what we got. Now we're converting this into 1.213 times 10 to the 5 Pascal per ATM. So then work done is equals to 162 joules. That means we have to convert everything into SI unit in order to get the value in joules. Okay. All right, so that means 162 joules of work was done. Now for part C, it says if 215 joules of heat was added into the system during this process, ABC process, how many of those joules went into internal energy? So we know that change in internal energy is equals to Q minus work done by the gas. So 215 joules were added, so it's positive. Then minus 162 joules that we just calculated, work done by the gas. That means we get here 53 joules. That means total of 53 joules of energy went into changing the internal energy. That means out of this much energy that was added to the system, 162 went into doing work, and only 53 joules went into actually changing internal energy of the system.